Atoms are the building blocks of the universe. Tiny particles that make up everything we see around us, from houses and guitars to rock musicians. They're so small that there are more atoms in a period than there are pencils in the whole world. If you could somehow look inside one of these atoms, you might see what it's made of. In the middle is a concentrated ball of material called the nucleus. Around the nucleus are tiny particles called electrons. These electrons spin super quick around the nucleus. Now this is the crazy part. The classical laws of physics seem to work fine for everything much bigger than an atom. But when it comes to really tiny stuff like atoms, the classical laws break down. The electrons don't fly around the nucleus in nice, regular orbits like planets around the sun. But instead, they are smeared out, taking on a cloud-like form.
What's that flaming ball in the sky?
And even weirder still, they are everywhere at once. Welcome to the quantum world. It's called the double-slit experiment, and physics professors love it because it's the perfect way to demonstrate the weird quantum behavior of tiny particles.
I'm going to tell you what nature behaves like, and if you will simply admit that maybe she does behave like this, you will find her a delightful, entrancing thing. So that's the way to look at the lecture, not to try to understand. I think I can safely say that nobody understands quantum mechanics.
Photons behave similarly to electrons, but because we can actually see photons as light, they're ideal for this experiment. The laser beam is filtered, so single photons fire off one at a time. The individual particles then arrive at a plastic barrier with two narrow slits. On the other side is a sensitive camera to show where the photons end up.
What you expect? You expect we'll hit two spots here, like that, or you expect the photon will go all over the map. Okay, you see the screen up there?
Yep.
That's what we see from the camera. See those individual flashes?
Oh, yeah, yeah.
Those are the photons.
Each flash of light is actually an individual photon hitting the back wall. They appear to be landing all over the place. But watch over time, and a pattern emerges.
Can you see somewhere in the middle of the screen?
It looks like a smudge.
Yeah, it looks like a smudge.
Yeah.
Those are the photon, where the photon hits. But it's not two, as we would expect. Is that weird?
Yeah, so why is that?
That's right, why is that?
Instead of the two bands that you'd expect, a series of smudges appears. It turns out that some photons land in a place on the back wall that would be physically impossible if they had traveled straight through just one of the slits. So on the quantum level, particles like photons don't always act like tennis balls. Instead, the pattern of photons matches what you'd get if you sent waves of water through the slits. It looks as if, while it's traveling, each photon spreads out into a wave, passes through both slits, then interferes with itself on the way to the back wall, where once again it acts like a particle, showing up in just one spot. Could this mean that as it travels, the photon goes through both slits? That it's in two places at once?
Now you're blowing my mind.
Good.
I was sitting over in, I think, a soft seat here, and Bohr was sitting about here, and I was just snoring over in the corner.
If Hugh's old pal Harvey had managed to stay awake, he may have heard the world according to Bohr. Bohr proposed that everything be divided into two categories. Big stuff, like tennis balls, apples falling off trees, obeys the classical laws of physics. However, small stuff, about the size of atoms, obeys the crazy laws of quantum mechanics. Bohr didn't stop there. He described what happens when you look at something very tiny. At that exact moment, the particle stops behaving so weirdly. Instead of being in a smeared out wave in many places at once, when observed, it's in just one place. It's now a nice, well-behaved little particle. The whole shebang was called the Copenhagen interpretation, and thanks to Bohr, became the established view. Oh, by the way, Copenhagen was Bohr's hometown. But the young and ambitious Hugh thought it was all most unlikely. How can just looking at something affect its behavior? Hugh was convinced that Bohr had it all wrong, and so he decided to start on his own radical theory, helped on most evenings by a sherry or two.
But
Mark's father wasn't the only one who found Bohr's theory difficult to swallow. So did the physicist Erwin Schrodinger.
as Schrodinger himself pointed out in a famous article, that there's something really weird about this idea of dividing the world into two parts. Because, you know, you are made out of atoms. So if an atom can be in two places at once, so can you, right?
Schrodinger had devised an experiment to expose this absurdity. He came up with the most famous feline experiment in science, Schrodinger's cat. It goes like this. A cat is penned up in a steel chamber, along with a radioactive substance, such as uranium, a Geiger counter attached to a quick-release hammer, and a flask of poison gas, hydrocyanic acid.
No.
Yeah.
At the heart of it all is a quantum event. Every now and then, completely randomly, there's a chance of a uranium atom decaying and emitting radiation. This radiation is enough to trigger the counter that sets off the hammer that breaks the vial that poisons the cat. But if none of the uranium atoms decay over the duration of the experiment, the cat will live.
What's so disturbing about this is fate of a single atom, right, determines the fate of a cat.
According to the Copenhagen interpretation, until the experiment is observed by peering inside, the entire contents of the box exist in two possible states. Each uranium atom both has and has not decayed. And still further, the poisonous gas has both killed and not killed the cat. And this is the paradox. A single cat that is both dead and alive at the same time. That's what Schrodinger couldn't buy, and neither could you. In the winter of 1954, sometime after the Bohr lecture, fortified by some sherry and a chat with Bohr's assistant Augie Peterson, Hugh came up with the theory of parallel universes. Hugh argued that everything in the universe, big and small, obeys the laws of quantum mechanics. And instead of the observer, Hugh introduced the notion of splitting. Splitting occurs every time a quantum event happens, and this is how parallel universes are created.
How does my father's theory solve the two different outcomes of the cat experiment?
It says that both outcomes actually happen.
The paradox had been that the one cat was both dead and alive at the same time. Hugh solved the problem with parallel universes, two cats existing in separate worlds, one cat dead, the other alive. Hugh's bold theory was backed up by some serious math. He was only 24 years old. Today, Hugh's ideas remain controversial, though a few physicists, like Max, see Hugh Everett as a visionary.
In my personal opinion, your dad's theory is one of the most important discoveries of all time in science. I just can't emphasize enough how important I think it is.